In an insulator, like rubber or glass, electrons are tightly locked to their atoms. Metallic conductors operate differently because of how their atoms are organized. Inside a metal, positive ion cores form a fixed lattice. Outer valence electrons break away, no longer tied to atoms. This electron gas moves in constant chaotic directions, colliding with ions while trapped within the material's boundaries. This internal mobility allows electrons to rearrange themselves. Because they are free to move, they easily respond to external forces applied to the conductor. Applied external electric fields force electrons to drift opposite the field. As electrons pool, exposed positive ions generate an internal field pushing back. This grows until it perfectly cancels the external field. All movement stops, reaching electrostatic equilibrium. Once a conductor reaches this equilibrium, it sets the stage for the specific physical laws that govern all metallic electrostatics.
The first rule of this state is that the net electrostatic field anywhere inside the conductor must be exactly zero. If the internal field were not zero, the free electrons would still be moving. Since they are at rest, we know the internal field has been neutralized. Gauss's law checks for charges inside the metal by measuring the electric field passing through an imaginary boundary, like this translucent sphere. Since the internal field is zero, no field lines cross the surface. The total electric flux is zero, regardless of sphere size or position. Mathematically, zero flux proves there is no net charge enclosed. This confirms that the interior of a static conductor contains no excess charge. If the interior must remain neutral, any newly introduced excess charge has to find a different location within the material. Identically charged particles repel each other. When excess charge is added to the metal, the particles violently push away to escape mutual repulsion. These charges flee the center until they hit the physical boundary of the metal. They have nowhere else to go, so they distribute themselves along the perimeter. In a state of equilibrium, the external surface of the conductor holds all excess charge. With the charge now trapped on the surface, we can determine the shape of the electric field radiating from the boundary. An angled field line resolves into a perpendicular force and a flat tangential force. This tangential force would pull surface electrons sideways, disrupting equilibrium. Because surface charges are at rest, no tangential force exists. The field must strike at a perfect 90-degree angle. The physical shape of the conductor's surface forces the surrounding electric field to remain strictly perpendicular at every point. These rules regarding the interior and surface relate directly to the energy required to move a charge. Moving a test charge through the zero-field interior requires zero work. Because there is no internal force to overcome, no energy is spent. Similarly, moving a charge along the outer perimeter requires zero work. The perpendicular field provides no tangential resistance to push against. Because no work is done moving between any 2 points, the entire volume and surface share the same electrostatic potential. The metallic conductor functions as a unified energy state. From the deep interior to the outer perimeter, the potential remains identical. The process begins when the electron gas reacts to an external field. They shift and lock into place until the internal field is zero, reaching equilibrium. This reaction forces all excess charge to the surface and ensures that all surface fields maintain a strict 90-degree angle. These individual properties are a single logical sequence. By understanding the metallic state, you can predict every other rule of conductor physics.